To plot this question, we're going to start with the relation between momentum and energy. So we know that we have E squared is equal to PC squared plus MC squared, where m is the rest mass of our particle. So from the values that we are initially given, we immediately recognize that we're only given momentum p and energy E. So we're going to need to square these values to get an equation that we're able to work with here. Because at the end of this, we're hoping that we can get some equation that is going to give us some variable times an x value, which we know is going to be p squared, plus some y-intercept. And if we go ahead and plot these values, we do indeed find just exactly that, where we have y is equal to 0.983 times our x plus 0.28747. And note that the units for all of this are in mega electron volts squared, because y is equivalent to E squared. So immediately we're going to notice a couple things, which is that if we are using x as p squared, then that means that this value here must be equal to c squared. And then we're immediately going to be disappointed when we go ahead and we take the square root of this and we find that c is roughly equal to 1. Well, that's not a coincidence, because the units we've been given don't actually use meters per second. They use C. So it makes sense that C is equal to 1C. So this might seem a little uninformative, but this illustrates that in a question like this, we don't necessarily get the most meaningful information out of this. But not to worry, we're going to be able to obtain an approximation for the speed of light later on using a few unit conversions out of this other value we have here, which we recognize as being the square of mc squared. So this is going to be m squared c to the 4. So if we go ahead and work with this, we can actually determine what our rest energy of this particle is going to be, or what the mass of this particle is going to be, in terms of units. So we're going to have some mass in units of mega electron volts per C. Sorry, apologies. We've listed our mass in mega electron volts directly. Not in mega electron volts per C. That would be units of momentum, which would get us kilogram meters per second. So this we can actually determine and convert over from mega electron volts to kilograms. We know that 1 mega electron volt is roughly equal to 1.78 times 10 to the negative 30 kilograms. A very, very tiny number, but quite meaningful for our purposes nonetheless. So if we go ahead and run our calculation here, we find that we're going to get a mass that we can work with. So let's go ahead and say that our mass is going to be the square root of 0.28747. Sorry, apologies. Initially, yes, this was mega electron volts per C squared. And that does make sense because these units do line up, that if we divide by C squared, we're going to get this conversion factor here. So if we go ahead and we take this over C squared, we are able to multiply by our conversion factor of 1.78 times 10 to the minus 30 kilograms, and we're going to get a mass that is approximately equal to 9.5 times 10 to the negative 31 kilograms. And that mass is just a little bit over that of an electron. So this experiment, quite useful for determining which particle we're working with. But now we want to go ahead and determine what the speed of light is, which we are going to be able to do by working backwards from here. So this time we want to work across the opposite direction. So we want to take our energy in mega electron volts and we want to convert it directly into joules. So let's say that we have our mc squared is going to be equal to our rest energy E. And this time we're going the other way. So we want C, which is going to be equal to, once again, square root of our energy E, which is 0.28747 mega electron volts, which we can convert to joules by going times 1.6 times 10 to the minus 13. That's going to get us units of joules, which, as we remember, are kilogram meters squared per second squared. And we can go ahead and divide that by the mass of an electron. And we can use either the mass we just found of 9.5 times 10 to the minus 31, or we can use a mass that we've looked up. Regardless, when we go ahead and solve this, we'll find a value for C that is roughly 2.2 times 10 to the 8 meters per second. Now, this value isn't stunningly close to the true value, which we know to be much closer to 2.8 times 10 to the 8 meters per second, but that shows the limitations of an experiment like this, which we wouldn't normally be using to calculate the speed of light, but rather to determine which particle we're working with, which in this case we did very well and we found to be an electron.